Good morning and welcome to this the lecture number 21 of the course Stochastic Hydrology. In the last lecture we dealt with the case study of Kaveri river flows at the KRS reservoir. We considered the monthly stream flows of the Kaveri river and then we plotted the time series, the correlogram, the spectral density, and then we went on to identify the model and we also looked at the validation of the model both for synthetic generation as well as for one time step ahead forecasting. Then we also considered the case study of a stream flow in a US river, American river, where the meteorology is entirely different and therefore, the contributions to the stream flow will be much different compared to the monsoon stream flows that we have in our part of the country. For the case study 4 again we plotted the time series, we plotted the correlogram, partial autocorrelation function and the power spectrum. Then we formulated several candidate models of the ARMA type. For each of the model we computed the log likelihood function, the mean square error and thereby identifying a model for synthetic generation of the stream flows as well as for one time step ahead forecasting using the mean square error criteria. Then we formulated the residual series and then on the residual series we did the validation test. Towards the end of the last lecture, I just introduced the case study of the Sakleshpur rainfall. The Sakleshpur region comes on the western Ghats and therefore, it has very high intensity of rainfall compared to the rest of the country in the rest of the country. So, we will continue with that case study today and see how the power spectrum appears like, and we also will go on to build an ARMA type of model for the Sakleshpur rainfall. As I mentioned earlier, we are considering the annual rainfall data here, but if you have let us say monthly data or daily rainfall data, typically the rainfall as the duration becomes shorter and shorter, it becomes more difficult to analyze the rainfall with linear models as we are doing now. So, typically the rainfall for shorter durations, specifically daily time steps or even weekly time steps etc., they are not amenable to analysis by linear models. But because we are considering annual rainfall data, let us see how the process itself behaves. Now, this is the time series. Compare this with the monthly time series of Kaveri river flows for example. Right at the time series plot, you would know that there are inherent periodicities present in the data. We have about 102 years of data for the Sakleshpur annual rainfall, and this 102 years data does not show, at least by examining the time series plot, it does not indicate that there are any significant periodicities present in the data. But let us see what happens if we plot the correlogram. The correlogram for this again indicates that there are no periodicities. In fact, these are the significant bands, 95% significant bands. Most of the correlations up to about lag of 25 were considered here, they are all insignificant. Only the first two and perhaps the third one appear to be significant. In fact, this is lag 0. So, you leave out lag 1 and 2 seem to be significant in this, whereas all the other correlations are insignificant. Because I have discussed correlogram I think about 4-5 lectures ago, let us recall how we formulate this. This is C k which is the covariance at lag k. You are considering the covariance between x t and x t plus k. So, x t minus x bar into x t plus k minus x bar by n, and then R k, which is the estimate for lag k correlation, you simply get it as C k by C naught, where C naught is the variance S x square of the process that you are considering. So, this is how you get R k. So, this is the plot between R k and k, and typically we go up to about 25% of the data. So, 0.25 n I have gone for the correlation. So, the correlation plot or the correlogram indicates that most of the correlations are insignificant. You may only have 1 and 2 as significant, and they are also decaying as you go with the lag. The correlations are decaying with the lag. Let us look at the partial autocorrelation. Again, as you can see here, there is only one partial autocorrelation that is significant, that is at lag 1. These are 95% significance bands. Similar to the correlogram, how do we formulate this? This is by taking 1.96 by n on either side of 0, or you can use it as a approximation 2 by root n, that is 1.96 by root n, or simply 2 by root n you can take, and n in this case is 102. 102 years of data is available, therefore, n becomes n. That is how you formulate the significance bands. The same significance bands you also use it for partial autocorrelations, because the number of data is still the same. As you can see, the partial autocorrelation at lag 1 only is significant, and at all other lags it is all the partial autocorrelation is insignificant. How do we get the partial autocorrelation? Recall again that we formulate the Yule-Walker equations. Yule-Walker equations will give you from this P p into phi p is equal to rho p. This is the Yule-Walker equation, where P p is the autocorrelation function and phi p is the partial autocorrelation and rho p is the autocorrelations. When you formulate the Yule-Walker equation of order p, you will get the partial autocorrelation for at that order phi p at that particular lag. So, corresponding to each of these lags, you formulate the corresponding Yule-Walker equation and get the associated partial autocorrelations. Then we also formulate the power spectrum. The power spectrum, again you compare this with the power spectrum that you obtained for monthly stream flows. This is annual rainfall that we are considering, and in a Western Ghats region. So, this is how the power spectrum appears. Again, recall how we formulate the power spectrum. I k, this is n is 102 in this case, alpha k you get and beta k you get from these expressions, where x t is your time series. This is time series. F k is 2 pi by n. So, you get corresponding to a particular k, you get f k, and t is the time, and x t again is the time series, and n is 102, and therefore, you get alpha k and beta k, and you get omega k, which is 2 pi k by n, and I am sorry, f k is k by n. If you recall from your spectral analysis, f k is k by n. So, associated with any given k, you can get f k, and t is simply time over which you are summing it up, and then x t is the original time series. So, you can get alpha k and beta k. Once you get alpha k and beta k, you get I k, and omega k is given by 2 pi k by n corresponding to each of these k, and this is the power spectrum that you get on this. Then we will see again, like we did for the earlier case studies, we formulate a number of candidate models. Now, the correlogram indicates that it is decaying either in a sinusoidal way or in an exponential manner. The correlogram may be decaying, and there may be 1 or 2 significant partial autocorrelations. Based on this, we suspect that this follows a AR model, AR type of model, that is autoregressive type of model. What we then do is, in fact, we could have used straight away the AR2 model based on the fact that there are 2 partial autocorrelations which are significant, and then the correlogram is decaying slowly, or in fact AR1 in this particular case, because we may be saying that there is only one partial autocorrelation which is significant. As you recall, there was just one partial autocorrelation which was also just on the borderline. If you look at the partial autocorrelation, you may have this also as significant, and this one is also significant. So, you may have one or two partial autocorrelations significant. You have the option of simply choosing based on correlogram as well as partial autocorrelation. But typically what we do, as I mentioned in the last lecture, is that we formulate a number of candidate models and then look at the likelihood values. So, the candidate models we consider in this case are AR1 to AR6 and then ARMA 11 to ARMA 32, 11, 12, 21 etcetera up to 32. Associated with each of these models, first we compute the parameters for taking by taking first half of the data. In the 102 years data, we take let us say about 50 years of data and then compute the parameters, that is the model calibration. So, calibration we do with the first half of the data and the parameters are estimated based on the first half of the data. Then we apply the model to the second half of the data and get the associated likelihood values. Remember, the likelihood value will have a E bar associated with it, that is the residual mean and so on. So, residual mean and variance you will get. The residual you will get by applying the model, any particular model, to the validation data part. In this case, the remaining 50 years or 52 years etcetera, depending on how much you have considered for the calibration. We obtain the likelihood values and we see that AR5 model gives the maximum likelihood and therefore, we choose AR5 for long term synthetic generation of the data. So, this is for the simulation of data. Then we also consider okay, fine, before I come to the forecasting part. So, AR50 or simply AR5, that is ARMA 50 or AR5, this model gives you the maximum likelihood value. The associated parameters for these are phi 1 to phi 5 and the constant. So, these are the associated parameters. Recall that we estimate the parameters by the Marquardt's algorithm or by the Armax function in the MATLAB. So, when we do that and when we were computing the likelihood values, the parameters for all of these models would have been estimated already, and with those parameter models parameters in place, we would have simulated the data and for the remaining part of the data, that is n by 2 values, and then obtain the associated likelihood values. Now, to summarize, the ARMA 50 model has phi 1 is equal to 0.40499 and so on up to phi 5, and then the constant turns out to be minus 0.30664. Now, we have identified this particular model to be suitable for long term synthetic generation of the data, and we also have the residual series with us. Now, we do the validation tests on the model. What are the 3 validation tests? If you recall, first of all, the residuals should have a 0 mean. So, the series of residuals that you get, you must first examine for the significance of the mean and must satisfy yourself that you can approximate the mean of the residuals to be equal to 0. Then we look for the periodicities, whether there are any significant periodicities present in the residual series. Then we also test whether the residual series that you obtain by applying a particular model is in fact white noise, in the sense that the residuals are all uncorrelated. So, these are the 3 tests that we do. So, first for the residual mean, recall from the last lecture how we obtain this eta e, and then this is again for the residual series, and for the 95% confidence level, the t value, t distribution value, n is in this particular case 102. So, you get for 102 values, this is n by 2 actually. So, we go with 52 values, because we have considered the first 50 values as for calibration. So, the remaining 52 values we are taking it for validation. So, you get t 0.95 corresponding to this as 1.6601 and therefore, the model passes the test, because the statistic that you have computed is less than the critical value of t, and therefore, the model passes the test. What do I mean by model passes the test? It means that the residual series has a 0 mean, or you can be confident that the residual series is insignificant. It has a insignificant mean. Then we look at the periodicity. Again, the first test of the periodicity, this is not the cumulative periodogram test. This is the first test that I introduced in the last lecture, where you look at the statistic eta and then compare it with f statistic, the critical value of f statistic with 2 degrees of freedom n minus 2. Again, n is in this particular case 52. So, you take 52 minus 2 and then get the associated f value, that is 3.085, and the eta values that you get corresponding to each of these periodicities, first periodicity, second periodicity, etcetera, will are all less than the corresponding f. And therefore, the residual series that you obtain from application of the ARMA 50 model, they are all insignificant. It has insignificant periodicities and therefore, it passes the test. Similarly, we look at the white noise test, and if you recall, it is the Whittle's white noise test, in which we formulate the eta again and then compare it with the f distribution with arguments. This is the degree of freedom n 1, which is a k max. K max in this particular case, we have taken it as 25, the lag, maximum lag that we have considered. So, this is 25 and n minus n 1, n is 52 and n 1 is 25. So, you get f 0.95, n 1 n minus n 1 as 1.783, and therefore, this eta being less than the critical value of f, it passes the test, and we conclude that the residual series that you obtain by applying the ARMA 50 model on the remaining half of the data passes the test of white noise, indicating that the residuals are all uncorrelated. Then we look at, remember what we did so far for this case study is for long term synthetic generation of the data. When we are interested in short term one time step ahead forecasting, we use the minimum mean square error criteria. So, we obtain corresponding to each of these models, we obtain the mean square error and then compare the mean square errors and pick that particular model which has the maximum which has the minimum mean square error. In obtaining these mean square errors, again we use the same parameter values that we had obtained earlier. In this candidate models, we would have obtained the parameters, the same parameters we obtain, and then we apply these models for the remaining half of the data and compute the mean square errors. If you recall, the error of forecasting, we are applying the model now one time step ahead. Let us say this being a yearly data, let us say we stand in a particular year 1985, let us say we stand at the end of that year and then forecast for the next year 1986 using these models, any of these models. Because we already have the data for that particular year, the forecasted value minus the actual observed value gives the error, or the actual value minus the forecasted value, does not matter, because we are taking the square of that, that gives the error E t, and that E t we square it and get the. So, here we get E t as x t minus x t cap. This is the forecasted value, this is the actual data, and this we are doing it for the validation time. So, E t you get, and then E t square you take divided by n, t is equal to 1 to n. So, this is how you get the mean square error. that is the mean square error that you are obtaining, and this is for the validation period. And then when we apply these models, this x t bar or x t cap is obtained by applying the a particular model. Forecast arising out of that particular model is denoted as x t cap there. And we choose here the ARMA 1-2 model as the best model arising out of the mean square error criteria, and this is what we use it for forecasting, one time step ahead forecasting. Let us see what are the parameters that we obtain for this. So, ARMA 1-2 we selected, and these are the parameters phi 1, theta 1, theta 2. How did we write the ARMA 1-2 model? So, the ARMA 1-2 model in this case we write it as x t. You have one AR parameter. So, I will write it as phi 1 x t minus 1, and you have two MA parameters. So, theta 1 E t minus 1 plus theta 2 E t minus 2 plus E t. This is our ARMA 1-2 model. So, you get phi 1, theta 1 and theta 2. So, these are the values. Phi 1 is 0.35271, theta 1 is 0.017124 and theta 2 is minus 0.216745 and constant is minus 0.009267. I must alert that we need to consider several digits of phi 1, theta 2 etcetera, because the x t will be quite sensitive to these parameters, and therefore, you consider several digits like 3, 4 or 5 digits you consider for each of these parameters. Okay, now, we apply this model now. Phi 1 is known, theta 1 is known, theta 2 is known, and E t minus 1, E t minus 2 etcetera, as I have explained on the application of the ARMA models, you use these as errors of the previous forecast. For example, E t minus 1 is the error of the forecast for t minus 1, E t minus 2 is the error of forecast for t minus 2. So, like this you do, and then when you are taking the forecast, what do? You do the expected value, take the expected value, and therefore, this term vanishes because it has a 0 mean. So, apply this for forecasting and formulate the error series E t, and then we do the tests on the error series now or the residual series. So, the first test that we conduct on the residual series is the significance of the residual mean, whether we can approximate the mean to be 0, and we compute the statistic, compare it with the associated t value, much the same way as we did for the calibration part, for the not for the calibration part, it is for a long term synthetic data, where we chose the ARMA phi 0 model. Similar test we can conduct on the residual mean for the forecasting model also. Then we also look at whether the residual mean has any significant periodicities present in that. So, we do the significance of periodicities, we examine several periodicities. Typically, these periodicities that we examine are obtained either from your time series plot directly or from the spectral density. In the spectral density, if you suspect that there are periodicities associated with, let us say 10 years, 15 years etcetera, based on the visual observation, you consider all those periodicities. So, typically we do for 5, 6 periodicities which are emanating from the spectral density, and then obtain for the residual series, obtain the eta values, compare them with the f statistic, in this particular case 2 and n minus 2. So, n is again 50 years of data, and then obtain compare the eta value with the f distribution to ensure that all the eta values that you have are less than the critical f value, and therefore, it passes the test for periodicity. Then the last test that we do is for correlations, that is, we have to make sure that the residual series that you obtain is in fact a white noise, or the residuals are all uncorrelated. So, this we do by Whittle's white noise test, and this is the statistic that we obtain 0.3605. Compare this for remember, for the Whittle's test you take n 1 and n minus n 1. Now, n 1 is the maximum lag. In this particular case it is, as I said, we would have taken 0.25 of n, let us say about 25 or something. So, n 1 in this case may be 25, this is also equal to k max. That is the maximum lag factor. So, you get the critical value of f as 1.783, and whereas your eta, the description of this eta I have covered it in the last lecture. Please refer to the Whittle's white noise test, and the associated eta value is 0.3605, and therefore, this passes the test because eta is less than the associated critical value of f. And we conclude that the model that we have chosen, namely ARMA 1-2 for one time step ahead forecasting, passes all the tests on the residual series, and we choose this particular model for one time step ahead forecasting. What I will do now is, for this particular case study 5, I will give you all the details of including let us say including how we formulate the models and the intermediate results, etc. Let me just go through the case study in some detail. This is typically we give these kind of projects as part of a course. So, when I teach stochastic hydrology for the master's degree at Indian Institute of Science, these projects are done by the course students. So, we give 10% or 15% weightage for this. So, the Sakleshpur rainfall data is given. I will also supply you the data with this, and then first you look at how the data appears by itself. Let us say you are looking at the time series, all of this I have explained. You also formulate the histogram. This is the original time series. You form the histogram. How do I formulate the histogram? You divide the data into several class intervals and look at the frequency, how many number of values have appeared in, let us say, between 1000 to 2000 and so on. So, like this you formulate the histogram. The histogram along with the time series gives you an indication of how the values are distributed. Then you form the correlogram. This is a correlogram associated with this, and then you also look at the partial autocorrelations. Then you look at the spectral density. Now, in this particular case, spectral density has been computed both with the Tukey window as well as the Welch window. The Tukey window is what I have explained in the class. So, look at all of these figures. These are for the original time series. Then we compute the MSE as well as the maximum likelihood values. So, this is why I am giving you all of this again repeatedly is that I will give you also the procedure by which you obtain these for residual series as well as for forecasting model and for the synthetic generation model. So, you get the MSE as well as the maximum likelihood values. You consider the 12 candidate models. Then we do the model validation. First, you would have got the parameters for AR5. These are the model parameters 1, 2, 3, 4, 5. 5 model parameters for AR, and then there is a constant. This is a constant there. Then we do the significance test. First, the test for residual series, which to examine whether this has a 0 mean. You get the eta value and the associated statistic, and then you look at the result whether this eta value is less than the associated statistic. Then you look for test for significance of periodicity. corresponding to each of these periodicities, you look at the eta value and the associated f 0.95 and make sure that all these pass the test. Then we look at the Whittle's white noise test. All of this I have discussed. So, let me go a bit fast. We have also introduced the turning point test, which I did not discuss in this particular course, but you can always go with the Whittle's white noise test for randomness. Then we look at the residuals. So, once the residuals have passed all the tests, we also look at the residuals properties themselves. The histogram of the residuals, the sample autocorrelation function or the correlogram, as well as the sample partial autocorrelation. These are for the residuals. Now, there is a concept called normal probability plot, which I have not discussed so far in the class. Maybe towards the end of the course, I will introduce this. This is to examine whether a particular data series in fact follows normal distribution or not. So, for the time being, you please do not worry about this, look at these three figures. So, this is on the residual series. Then again you look at the ARMA 1-2 model, which we selected for one time step ahead forecasting, do all the tests again, do the test on the residual series to examine that it has a 0 mean, it has insignificance of periodicities, and then it also passes the test for randomness or the white noise test. And then we also look at the plots of the residues themselves. Now, these plots of the residues as well as the original time series give us important insights into how the particular model is behaving. Now, what we do is, let us say we have chosen the AR5 model as the model to be used on this particular case study for long term simulation of data. So, we apply that model for let us say about 100 years, 150 years, we simulate the data and then compare the various statistics of the simulated data with those statistics of the original data. So, essentially what we do now, we have chosen AR5 model for synthetic generation of the data. We have estimated all the parameters. We have convinced ourselves that this model passes all the tests, and therefore, this model is now ready for application. Let us apply this model now. So, we apply this model to simulate a large number of data belonging to that particular time series. So, and then we compare the statistics. So, remember this is for the original time series, and then we have simulated, it is not for validation period. We have done all the validation tests, kept the model ready now. Now, we simulate for next 100 years, one sequence, two sequences, etcetera, like this. Next 100 years, we simulate the data and then compare the data, the mean of the original simulated series with the original series. So, this compares like this. Similarly, the standard deviation compares 488, 590. Then there is a skewness minus 0.01867 and this is 1.167, kurtosis 2.90, 7.56. It may appear that the model is not reproducing well the skewness and kurtosis, but it was not meant to in fact. You see, there was no feature in the model that that would reproduce these statistics. But however, for comparison purpose we have still used this, because in certain situations you would like the particular model to reproduce certain statistics. For example, skewness, if the skewness in the original data was significant, you would like to preserve that kind of a skewness in the final simulated data also, in which case it is better to compare them. So, while you have not built the model to preserve the kurtosis and the skewness specifically, but the model that you are actually applying for long term synthetic data, you would be curious to see whether the skewness is preserved at all. and in this particular case skewness as well as the kurtosis are not well simulated, whereas the mean and standard deviation we can take them to be acceptable. So, we now compare how the original time series and the synthetic data appear to be. So, this is for the original time series, the left side what you are seeing is for the original time series, these are all for the original time series, and this is for the simulated data. You can see some similarities, not so much in the time series itself, but if you look at the histogram appears to be similar in some sense here in terms of the distribution of the data. Remember here the scales are different, this is 500 to 3500, whereas here it is 0 to 6000. So, that is why it appears to be slightly wider in this case. Then you also look at the partial autocorrelations. The partial autocorrelations seem to be I am sorry, this is a correlogram seems to be reproducing it well. In fact, the time series model this is AR5 model and therefore, the information on the correlation will be well preserved in the original data in the simulated data with respect to the original data. Now, in this file here PDF file, I have given you the complete data. This is the station is Sakleshpur, state is Karnataka, basin is Hemavati, the source is earlier it used to be called as drought monitoring cell, now it is called as disaster management cell or some similar name, it is located in Bangalore. So, we have obtained the data from this source and this data I am giving here. You can use this as an exercise. So, take this data, do the complete time series analysis, you have the data from 1901 to 2002 here. So, you will use this data and do the time series analysis that I have discussed in this particular case study, and satisfy yourself that you get all of these values correctly. All right, now we will try to summarize what we did in the case studies. Let me give the summary of the results that we obtained for various case studies, so that you get a physical feel. Remember, I have discussed the case studies only for rainfall and stream flow at different time steps, but you should be able to do the same analysis on let us say evapotranspiration. If you have a large number of data corresponding to evapotranspiration, you can do the same type of analysis. Several cases do exist in literature where the time series analysis has been applied to water quality parameter, water quality indicators, for example, dissolved oxygen at a particular location. If you have a series of dissolved oxygen values at a particular location and the stream has stabilized in the sense that in terms of the effluents that it is receiving and in terms of the hydrology etcetera, it is stabilized and you are only looking at the particular water quality indicator time series, then you choose that data and then apply the data to carry out the analysis that we have discussed. Similarly, there may be other variables, for example, groundwater fluctuations. If you have groundwater levels at a particular location for a significant length of time, then you use that as a time series, apply the techniques that we have just discussed and then build models for forecasting how the groundwater levels at that particular location are likely to behave, and similarly you can build models for synthetic generation of the groundwater levels. So, many of the hydrologic variables that we will be interested in making decisions or in making long term plans can be analyzed using the time series techniques that we have discussed. So, before we close the topic on the time series analysis, let us summarize the case studies themselves. So, first we considered the Bangalore city daily rainfall data. So, this is how the daily rainfall data appears. let me come back to that. So, we started with daily rainfall, then we went on to aggregate the daily rainfall to get the monthly time series, then aggregated the monthly rainfall to get the annual time rainfall time series. So, this is how the daily rainfall data appears. There are a large number of values and you can see that you may not be able to see any significant periodicity. There is no periodicity when you are considering the daily rainfall data. Whereas, if you look at the monthly rainfall data, there appears to be some smoothing and therefore, you may suspect that there may be some periodicities present here. Again, if you aggregate the monthly data and then put it into an annual time series, again the periodicities have gone. So, both in the daily rainfall as well as in the annual data, you may not see any periodicities. Then we formulated the correlograms corresponding to each of them. Let us compare the correlograms of the Bangalore city rainfall. This was for the daily rainfall, this is for the monthly rainfall and this is for the annual rainfall. As was suspected in your time series data, we thought that the daily rainfall may have the monthly rainfall may have some periodicities present in the data. These are confirmed by the correlogram. The correlogram indicates that there are periodicities here. The correlogram is oscillating in a sinusoidal way. So, there are periodicities present, whereas most of the correlations here in the daily case are all insignificant. Similarly, in the annual case they are all insignificant. We went on to plot the spectral densities for each of these cases. The spectral densities appear like this. For the daily rainfall, the spectral density appears like this, indicating that there is no single frequency at which a large contribution to variance takes place. So, this is more or less like a white noise, whereas the monthly periodicity, monthly data throws up some significant periodicities. One corresponding to 12 months is quite significantly different from those corresponding to 6 months and 4 months. Whereas, again the yearly data does not show any preference for any particular frequencies. The high frequencies seem to be dominating here, but there are no significant periodicities thrown up by the yearly data spectral analysis. Then we consider the Kaveri river flow and a stream flow of a US river here and also Sakleshpur annual rainfall data. So, these were the time series plots. This is just to show how the time series may appear differently for different types of variables and different types of locations. For example, monthly stream flow time series of a monsoon climate typically appears like this, where you can see that there are some oscillations in the data here, whereas here it may show certain trend here. There may be slight increasing trend that is seen here. And this is the annual data. Annual data does not show up any periodicities or does it show any nor does it show any trend here. So, this is how the different time series appear on a visual inspection. Let us look at the correlograms also. The monthly time series of the Kaveri river yields a periodic or the sinusoidal type of correlogram, and the monthly stream flow data of the US river, this also shows periodicities, but there are many of the negative periodicities which are negative correlations which are all insignificant, and both of them show a slow decay. This correlogram shows a slow decay here, this also shows a slow decay in the correlograms. The Sakleshpur annual data on the other hand shows there is only one significant correlation and all of the remaining correlations are all insignificant. Remember, lag 0 is always 1, the correlation at lag 0 is always 1, and therefore, you look at only lag 1 and beyond, all the correlations here are insignificant. So, the rainfall typically behaves much different compared to the monthly stream flows. This is what we observe from here. Then we look at the power spectrum. Power spectrum essentially confirms our suspicion that there are periodicities present in the monthly stream flow data. So, you see that there is a periodicity associated with WP of 0.52 or some such thing, which corresponds to 12 months. This is 6 months, whereas the 12-month periodicity is absent in the river that I have considered from US. So, there is no 12-month periodicity here, whereas there is a 6-month periodicity, there is a 4-month periodicity. Now, this 6-month periodicity appears to be quite significant for the monthly stream flow of a western river, whereas in the peninsular Indian river, the 12-month periodicity almost always comes out to be significant. Whereas the Sakleshpur annual rainfall data does not show one periodicity to be any different from any other periodicity, although here it appears to be that the lower frequencies are dominating. And then we went on to build models, the ARMA type of models for the monthly stream flow data. For data generation, we got AR4 model, and for one time step ahead forecasting, we got AR1 model, that is ARMA 40 or ARMA 10 model. Then for the monthly stream flow data of a river, whenever I say a river, this is we have taken it from the web from USGS site. So, this is available from the USGS site. This is a US river. In fact, those of you who are willing to experiment on different data sets, this is a good site from which you can download the data, time series data, and then do all your all the analysis that I have discussed in this course. Unfortunately, such a data is not very freely available in India, and therefore, you may not be able to do all these analysis that I have discussed satisfactorily with the Indian data, unless you put extra effort and obtain data from several sources who are the custodians of the data in the country. Now, for the monthly stream flow data of the US river, we got AR80. Remember here, these type of models that we are getting themselves show the difference in the processes that have contributed to getting that particular time series. So, as I mentioned, in the peninsular Indian region, essentially the stream flows are generated by the monsoon rainfall, and therefore, you get a significant periodicity. Every year you get some kind of a regularity, that monsoon months have higher flows compared to non-monsoon months and so on. Whereas, if you look at time series of stream flows in, let us say, European region, that may be much different from the peninsular Indian region, which may be much different from a US river and so on. So, it depends on how what kind of physical processes are in fact generating the particular time series that we have observed, and based on that you get different types of models coming up, because the dependence of values observed at a particular time on those observed at some other time depends on the type of physical processes that are governing that particular process. So, you get a 8-0 model for both data generation and one time step ahead forecasting, which may be quite surprising to those who are working on especially peninsular Indian rivers, where we typically get models of this type, and especially for forecasting we often come with ARMA 11 or 10 model or maximum 2021 type of models for one time step ahead forecasting. Whereas, for monthly stream flow data of the US river, you get a ARMA 80 model both for long term simulation of the data as well as for one time step ahead forecasting. Then for the Sakleshpur annual rainfall data, remember rainfall data behaves much differently from the stream flow data. Stream flow is a much smoothened process. we get a model of ARMA 50 for data generation and ARMA 12 for one time step ahead forecasting. I have provided the data for this Sakleshpur annual rainfall, and I encourage all of you to go through this data, do all the analysis that I have discussed in this particular course with that particular data. If you do not have access to any other data, use that particular data and then do all the analysis. So, with this now we conclude the discussion on time series analysis. This is the right time to just quickly summarize what we have covered in the time series analysis. So, we form the series x t and then we discussed about the stationarity of time series, and we also introduced the concept of ergodicity of time series when the time average properties are same as the ensemble average properties are the same as time average properties. Then we say the process is ergodic, and then we went on to build time series models. We also discussed analysis in the frequency domain, where we express the time series with frequencies, and then we did the spectral density, we did the spectral analysis. Spectral analysis essentially shows up the periodicities present in the data. We discussed correlogram, that is autocorrelations, autocovariance function, then we introduced the concept of partial autocorrelations, and then went on to build ARIMA type of models. So, first we have to convert the time series into a stationary time series. So, the models that I have discussed are all stationary time series models, and the type of models, specific models that I have introduced are in addition they are all linear models, because how do I write ARMA 10 model? We write it as x t is equal to phi 1 x t minus 1 plus E t. So, they are all linear models, there are no nonlinear terms. We specifically introduced the differencing to make the non-stationary time series, to convert the non-stationary time series into a stationary time series. So, we looked at first order differencing, second order differencing and so on. That is, how do I write the first order differencing? It is x t minus 1, that is all. So, simply take the difference of a particular value with that of the previous value. The second order differencing will be x dash t minus x dash t minus 1. So, that is how, where x dash t is the first order differencing. So, this is how we do the differencing. Typically in most hydrologic time series, if you do first order or second order differencing, the series can be converted into a stationary time series. However, there may be periodicities present in the data, in which case you may have to account for these periodicities in the time series models that you consider, and that is where we look at both contiguous as well as non-contiguous type of ARMA models. So, we identify the AR components and MA components essentially by the plots of correlogram and partial autocorrelation functions, and also the spectral density. So, there is a procedure of identification of the models, then calibration. In the calibration, we discussed the estimation of parameters, although I did not cover the algorithm of the parameter estimation. I have given you the Rmax function, the syntax, which you can use on MATLAB and then estimate parameters for any of the ARMA type of models. So, first we do the differencing. ARIMA, remember ARIMA is autoregressive integrated moving average models. Now, that integrated I refers to the differencing. So, the order of differencing. When I say ARIMA P D Q model, we have AR terms of order P, differencing of order D and MA parameters of order Q. That is how we write ARIMA P D Q models. So, first we do the differencing, and then on the difference series you apply the ARMA models. So, Rmax function of the MATLAB gives you the parameters of ARMA type of models. Then we discussed how we obtain the likelihood values corresponding to each of the ARMA models, and also the mean square error, which means that in the calibration period we take a part of the data, typically the first half of the data, and then estimate the parameters, apply the particular model for the next half of the data, validate the model. By validation I mean you obtain the residual series and make sure that the residual series passes all the tests, namely that there are the mean of the residual series is 0, there are no significant periodicities present in the residual series, and also that the residual series is uncorrelated or it forms a white noise. So, these are the 3 tests that we do on the residual series. So, we now know for a given time series how to get a time series model or the ARMA type of model, both for synthetic generation of the data as well as for one time step ahead forecasting. So, we will close this discussion today on time series analysis. In the next lecture, I will introduce the Markov chains, which is a slightly different topic from what we have been doing so far. So, we will continue the discussion in the next lecture, where I will start with discussion on Markov chains. Thank you for your attention.